In this video, we're going to talk about continuity. Basically, we're going to talk about what is a continuous function and the different types of discontinuity. So first off, we say that a function f is continuous in a set A if f is continuous at every point of an interval A. More, we just say that f is continuous, we mean that f is continuous at every real number. So if you simply say f is a continuous function, that means it's continuous everywhere, for every real number there is. There is an intuitive way of talking about what continuity is. Basically, and let me grab a little pen. If you're talking about a function, and the easy definition to kind of remember is if you can draw that function without picking up your pen, it's a continuous function. If while you're drawing that function, you have to pick up your pen, you continue drawing it, it's not a continuous function. And this x value here is where we would have discontinuity. That's where the function would be discontinuous. Okay. So let's look. There's three things that have to hold true for a function to be continuous at a point. We're talking about a point x sub 0 or x naught. It's another way of saying it. First off is f of x sub 0 has to be defined. So if it's a function where it's not defined, then it's going to be discontinuous. So if we have a function f of x is equal to 1 over x plus 2, we know that the function is not defined when x is equal to negative 2. And so this function is going to be discontinuous at x equals negative 2. Okay. Let's clear that off. The other thing is that the limit as x approaches x sub 0 of f of x has to exist. If it does not exist, remember that means that it's going to two different points. So maybe it's going here and here. It's going to be discontinuous, right? There's a gap. There's a jump that's happening there. Other option is, what if it's going this way? What if it's going that way? It's discontinuous, right? One's going to positive infinity, one's going to negative infinity. There's a gap in there. And then the last thing that has to hold true is that the limit as x approaches x sub 0 of f of x has to equal the same value as f of x sub 0. So basically, you can't have something like this. Here we have a function. Let me draw it real quick. So let's say comes here, you have a hole there, boom. And then we have a dot here. So here, let's say this is f of, I don't know, 3. It's equal to 4. But the limit as x approaches 3 of f of x is equal to negative 2. So the limit exists. It goes to the same value on both sides. And the function is defined for that point. But what it equals at that point is not the same as the limit. And so it's discontinuous at that point. It's discontinuous at x is equal to 3. I mean, you can see you would have to pick up your pen and put the dot there. So yeah, that would be discontinuous. So let's look at the different types of discontinuity. Discontinuity of a function f at x sub 0 is called removable when f of x sub 0 is defined and changing the value of the function at x sub 0 produces a function that is continuous at x sub 0. So that example we were just looking at, let me get rid of all the highlights I did. If we change the definition, if we come in and we make like a piecewise defined function such that f of 3 is equal to negative 2, then that would change. That would put this value here now. Get rid of that. So if we change that one value, now it would be a continuous function. That's a removable discontinuity. We can remove it by just changing the definition at one value. Another thing that can happen is jump discontinuity. So that's the example basically we were seeing where you have a function and down here it goes to this, up here it's here. That would be jump discontinuity. For a function f of x, f has a jump discontinuity at point x sub 0 in its domain provided that the following are true. The limit as x approaches 0 from the left of f of x is equal to L1, which is less than infinity, and the limit as x approaches 0, x approaches x of 0 from the right of f of x is equal to L sub 2, which is less than infinity. And it has to be true that both limits exist and L sub 1 does not equal L sub 2, so they don't go to the same value. Basically, the limit doesn't exist. In more simple terms, a function f has a jump discontinuity at x sub 0 in its domain if the limits from the left and the right side are not negative or positive infinity, and the limits from the left and right side are not equal. That's all you need. So let's look at these nice little graphs that I was able to find. And you can see it's basically the thing that we were talking about here. For removable discontinuity, the limit exists and it goes to the same thing. Well, it has to go to the same value from both sides, left and right, but it just jumps up here to that one dot. But if we change the definition of the function for that one dot, it would make it continuous. And so that's a removable discontinuity. Here we have a jump discontinuity. From the left-hand side approaches that value, from the right-hand side approaches that value. F of x is defined, it's just that dot right there. But there's a jump happening. The limits aren't going to infinity, and so it's going to be a jump discontinuity. And an infinite discontinuity, from the left, it's going to infinity. From the right, it's going to negative infinity. And so there's a break, there's a gap happening, a jump, but they're going to infinity. So it's a infinite discontinuity. All right. And that's it for some quick notes on discontinuity. We're going to look at some examples of the three on the other videos. I'll do a video for each.